Hi Carbon Time teachers, it's Jenny again. This presentation will explain our approach for designing the Carbon Time units, what this structure means for your teaching, and also introduces you to the Carbon Time units by using systems and scale as an example. So hang tight, fasten your seatbelts. This is a lot of information, but feel free to watch this video more than once and to pause the video to read and review materials, or to send me an email, or even to set up a phone call. The goal here is to give you a broader view of what the units are about and to get you ready to teach Carbon Time. So first, it takes more than one lesson to achieve meaningful objectives. So this is activity sequences are what we're going to talk about next, and this is about what connects your classes from one day to the next, and how to keep your students thinking about the big ideas. And the big ideas are things like matter conservation and energy conservation, and linking what they see in everyday life to its underlying chemistry. By the way, you get some awesome photos when you Google students thinking, which I had a lot of fun with. Anyway, maybe you've heard of teaching sequences before, or activity sequences. Another common one is the 5 E's for inquiry. To talk about teaching sequences, we can start with what it looks like when a teacher is not using teaching sequences. It may be that as a teacher I would need an activity on cells, and then one on organelles, then one on enzymes, and the activities are chosen because they look exciting, but maybe not necessarily connected with ideas. Another way teachers might connect lessons is procedurally, like today we're on chapter 4, tomorrow we'll do the lab on page 37, and then implicitly there's a message to students, which is science is mostly about grades and procedures and following the textbook, and learning science is mostly about procedural display, or spitting back to the teacher whatever she tells me without any connections. And that's not what you want, those two types of teaching. What you want is to connect to the big ideas for all your classroom activities, and to support the learning of the big ideas by teaching a connected sequence of activities. So, before we go much further, I recommend that you download and reference or print out these 3 documents. One document, Units at a Glance, gives you an outline of the lessons and activities. The unit learning goals describes the learning goals for your students in every unit. And the Carbon Time activity sequence document will give you useful information to reference about the structure of the units. And the 2 appendices are items that I'll refer to throughout this presentation. So I would even pause me right now and grab these documents either digitally or on paper. They're located both, all 3 are on the group spaces under the Files tab, or on the National Geographic web page on the Program page, and any of the unit pages. So especially have ready the parts about the systems and scale unit, which I'll use as an example in the video. Okay, go do it. Okay, so do you have your learning goals document? So the learning goals, so for the first 4 units, there are learning goals that are associated with each of the different carbon transforming processes, which are these: combustion, biosynthesis, and digestion, cellular respiration, and photosynthesis. And each unit has a learning goal about inquiry, which includes measurement, arguments from evidence, and collective validation through pattern finding. So pause and read about these learning goals specifically for systems and scale. They have to do with measuring the mass of fizzing soda water and burning ethanol, detecting changes in carbon dioxide with BTB, and then finding patterns in the data and connecting these patterns to an explanation about chemical change and combustion. Okay, so there are also learning goals about application that are aligned with each of the 3 questions, which we've been talking about off and on. The 3 questions, capital T, capital Q. So this is where students take what they know from inquiry and then add learning from the molecular model kits and molecular modeling activities. And then they apply, that's why this is an application part, they apply this knowledge to an explanation of carbon transforming processes. So you can pause now and read about these learning goals, especially for systems and scale, to give a sense of what these look like. Okay, so here's where I want to introduce or reintroduce to you the 3 questions. So this is our scaffolding that will help students give complete explanations of carbon transforming processes. So a complete explanation of something like combustion addresses where are the atoms moving, what's happening to carbon atoms, and what's happening to chemical energy. And you can read the rest of the questions that are associated with those 3 questions. So the rules to follow are rules that you as a teacher set up in the classroom and ask students to follow each time they attempt to explain a carbon transforming process. So the first rule is that carbons last forever in combustion and living systems, and all materials are made of atoms. So this basically means that atoms cannot be created or destroyed and that matter is conserved, and keys in for a student to trace matter through systems. And the evidence that a student should look for when doing inquiry investigations especially is that if a material changes mass, that means that atoms have moved, or that when materials move, atoms are moving. So this especially keys into the weight and mass data that students collect. Another rule that students need to follow is that atoms can be rearranged to make new molecules. So atoms are forever, but molecules are not forever. So when a student is doing inquiry investigations, they'll be measuring CO2 with BTB. For example, in the animals unit, they're detecting CO2 as a result of mealworms doing cellular respiration. And in order to trace where that CO2 comes from, the student needs to know that the carbon atom must have come from somewhere, but the carbon atom could have been in a different kind of molecule. For example, it could have been in an organic material like a food or a fuel or a living organism. So students do molecular modeling to reveal what molecule carbon dioxide was in the carbon atoms and the oxygen atoms, what molecules those atoms were in before the mealworm did cellular respiration. So specifically, they trace the carbon atom from the carbon dioxide to molecules within a living organism. So a third rule to follow is that energy lasts forever in combustion and living systems, and that carbon to carbon and carbon to hydrogen bonds have more stored energy than carbon to oxygen and hydrogen to oxygen bonds. During inquiry investigations, students can observe certain forms of energy like light and motion and maybe heat. But to determine if something has chemical energy, they need to look at the atomic molecular level to see if molecules have carbon to carbon or carbon to hydrogen bonds. So when students do molecular modeling, they learn that organic materials like foods, fuels, and living and dead plants and animals all have stored chemical energy. So these are the 3 questions and the rules to follow and how those connect with the inquiry investigations and the molecular modeling. And as we walk through the units, hopefully it will become more apparent how that works. So we're going to walk through these steps that appear in all of the units. So here they are in brief, so you know where we're headed, and then we'll go into more deep depth with each one. So first of all, there's formative assessment for each student, that's the pretest, and then establishing a problem for the whole unit. Next, in all the units, there's foundational knowledge and practice, where you're giving the students a little bit of information that they're going to need throughout the rest of the unit. Third is the inquiry activity sequence, which is predict, explain, observe, explain. We'll get into that. And then the application activity sequence, which is basically model, coach, fade. We'll talk about that soon too. And then there's a final assessment where you check your students' understanding in a summative way. Okay, so just in general, the information about the step in the activity sequence can be found on the National Geographic site under the Objectives tab, and then under Teaching Approach. I wanted to point that out to you because it might be a little bit buried. And in the next part of this presentation, I'm going to walk you through systems and scale. So now would be a good time to look at the Carbon Time Activity Sequence document and to flip to the 4th page, which is Appendix A. Okay, so, oh, there's a picture of what it looks like. Okay, so let's walk through systems and scale. In all of the units, lesson 1 is the formative assessment for the rest of the unit and also helps establish the problem for the unit as a whole. So for example, in systems and scale, first students take the pretest in activity 1, and then in activity 2, the problem is established by the teacher doing a demonstration of ethanol burning and then showing that water looks the same, has the same macroscopic features, everything that we see looks the same, but it doesn't burn. So ethanol burns and water doesn't burn, and what's going on here? And then the student thinks about that and records their ideas about what happens when ethanol burns. And then the student revisits these ideas later in the unit. So in all of the units, lesson 2 is about establishing some foundational knowledge and practice for the students that they'll need throughout the rest of the unit. For example, in systems and scale, first students watch and discuss the classic Powers of 10 video. And I say classic, I think it was made the year I was born, yes. But still very interesting and important, and sets up information very well for the students. And then in activity 2, which is optional, students learn about the benchmark scales, which is the atomic molecular scale, the microscopic scale, macroscopic scale, and large scale. And get some practice sorting these items into these scales. So this is optional. We consider it optional because it might be too simple or easy for high school students. But of course, you're welcome to do it as a middle school or high school student. All right, so then activity 3 also introduces the benchmark scales to a certain extent as well. And then students learn about what air looks like at each of the 4 scales. So you zoom into air and look at molecules. And then activity 4 is a quiz for students to help check their understanding of the knowledge and practice from lesson 2 before they go on to the rest of the unit. So this is a quick check for understanding for your students. Okay, so just a note to say, lesson 3 in systems and scale is optional, especially for more advanced students. And it's an inquiry activity sequence for soda water fizzing as a way to introduce students to chemical change. But because the structure of the soda water activity is similar to the structure of the ethanol burning activity in lesson 4, I'm going to skip to lesson 4 and just talk about the ethanol burning, which is recommended for all students. Okay, so before we go on to lesson 4 though, just a little bit about inquiry. Educators use the word inquiry a lot, and I wanted to give you our definition of inquiry. So sometimes the word inquiry is used to denote almost any kind of activity that's hands-on or that is student-centered and gives students choices. And our definition of inquiry is a little bit more specific. Yes, I think I need to rewind. So here actually is the steps of the inquiry sequence. Sorry, I skipped ahead a little bit. So first, students predict what will happen during an investigation and explain their predictions. And then students observe what actually happened, so they gather their data. And then they clarify it and explain what they've observed. So this is where the predict, explain, observe, explain comes from. Sometimes we shorten it by saying the PEOE sequence. And so one of the reasons we have them explain twice is because the reasoning is the hardest part. And so they have to do it first when they form their initial ideas and predictions, and then again when they, after they create their data and their observations. Okay, so now I'm going to talk about how we define inquiry. Okay, so the way that we define it is, first, one way to decide whether an activity is inquiry is to consider the source of students' knowledge or the answers to their questions. Who's the authority? Is it the teacher or is it the data? And is the student the one who's collecting the evidence and doing the pattern finding? And so when students are finding and explaining patterns in evidence to learn, we consider that inquiry. Oh dear. Okay. And then secondly, inquiry involves developing arguments from evidence. So it might not necessarily follow the specific steps of the scientific method because it depends on the type of evidence and how it was collected. But either way, there is an argument that develops and emerges from the evidence. Third, it's connected to content learning goals. So we have a lot of scaffolding in our units that explicitly links the inquiry activity to content learning goals and tells us what the inquiry can say about a carbon transforming process and what it cannot say to about a carbon transforming process. So the inquiry activities within our units answers some parts of the 3 questions, but it doesn't tell us the full answer to the 3 questions because the inquiry activity happens at a macroscopic level, and we need to know more about the atomic molecular level to give a complete explanation. So that's part of what the 3 questions does, and also the unanswered questions, which we'll get to in a second. And a misconception about student inquiry is that it necessarily involves putting students in control or giving them complete freedom to explore. But we think that students often need a lot of scaffolding in order to do productive inquiry. And so we've added some scaffolding to the inquiry investigations in our units. Okay, so finally, let's get to systems and scale. Here's an example of the PEOE sequence in systems and scale. And so now we're skipping to lesson 4. So for ethanol burning, in lesson 4, activity 1, the students revisit their initial ideas from lesson 1 about what happens when ethanol burns, and you will have recorded their initial ideas about that. And then they discuss the investigation tools, and they watch one of our awesome videos about the investigation. And then they make predictions about what they think will happen to the weight of ethanol and the color of BTB. And now you could pause if you'd like and go watch our cool new video in lesson 4 on the National Geographic webpage. And you can see here one of the really catchy parts. I won't ruin the surprise for you. I'll let you go watch it. It's fun. All right, so activity 2 in lesson 4, the students set up the burning ethanol investigation. And in this case, in systems and scale, because the investigation takes about 20 minutes, while the students are waiting for the results, they can write down their predictions that they thought about in the previous activity. So even though the predictions come first, we've rearranged the activity a little bit so that the writing, the actually time part, is timed so that you can be more efficient with your time in this case. Okay, so the investigation includes weighing ethanol before and after burning, and then burning the ethanol under a container, which you see in the picture, with a petri dish of BTB. So the BTB turns from blue to yellow, which indicates an increase in carbon dioxide concentration within the container. And so teachers, feel free to try this at home with the materials that we sent. When you put the container on top of the ethanol, the flame goes out pretty quickly. But we also recommend that you put a little bit of aluminum foil on the top, just in case, but it definitely doesn't get so hot in there that the plastic melts. You don't have to worry about it. And then lesson 4, activity 3, the student gives an explanation of burning ethanol in context of the 3 questions. So they answer, for ethanol burning, where are atoms moving, what's happening to carbon atoms, and what's happening to chemical energy. And then you can kind of see in this worksheet, they draw arrows to show how atoms move into, through, and out of a flame based on what they learned in the investigation. Okay, so here's where we're going to talk a little bit more about the unanswered question. So each unit has an important connection between inquiry and application. And so, like I said earlier, the inquiry investigation occurs at a macroscopic scale, while a complete explanation of the 3 questions, using the 3 questions, includes the atomic molecular scale. So the inquiry investigation answers some questions, but not all. So for example, where are atoms moving? The students learned that atoms are moving away from the ethanol because the weight of the ethanol decreased. So that the first question about where atoms moving is pretty well answered by the inquiry investigation. What's happening to carbon atoms for that question? Students learn from the inquiry investigation that carbon dioxide is produced because BTB turns yellow. But one of the rules for carbon time is that atoms are forever. So where did that carbon atom in the carbon dioxide come from? An unanswered question is, where does the carbon in the CO2 come from? And what molecule was it in before the change, before the burning? And then the third question, what's happening to chemical energy, is partially answered by the inquiry investigation because we see light and heat, but because energy lasts forever, that energy must have been around before the ethanol burned. So what form was the energy in before it was light and heat? So those are the two unanswered questions that bridge the inquiry and the application activities. So the application teaching sequence or activity sequence is here. So this is to give students repeated practice with a skill. It helps helps students master activities that are complex or difficult for them. So this is really important, especially when a practice is complex and difficult. So you could think of an apprenticeship type practice like cutting hair, for example, and we liken it to something like that. So it's important for you as a teacher to remember that the way this application activity sequence works is that first activities are highly scaffolded, and then students take on more responsibility throughout the activity sequence. So it starts with establishing a problem, and then modeling, coaching, fading, and then one more is maintaining. And so let's look a little bit more in depth about what this is. And you can think about this in terms of your own classroom. So how well do these relate to how you think about learning in your classroom? So first, establishing the problem. So the goal for the student is to talk about relevant ideas and experiences, to set up the expectancy for the student that they are capable of understanding, and to establish what you value, and establish interest and relevance of learning. And so here, this is where we're eliciting student ideas about discrepant events like burning water versus ethanol. And it might be that we discuss connections to previous units or previous learning. And then in modeling, the goal is for students to see and understand how an expert accomplishes the objective and to understand what they know and what they still have to learn. So in a classroom, this might look like think aloud problem solving, or using contrasts between scientific thinking and more naive thinking, or like what we do mostly is by using models, which is what we do when we're doing the carbon time molecular modeling. They're able to see how an expert accomplishes the objective by thinking about the molecular models or an atomic molecular level. So coaching. So here is where students get practice using scientific ideas to accomplish an objective, but with support and feedback. So this is a little bit more, scaffolding removed, a little more withdrawn from the teacher. And so this could be activities where you're focusing on student misconceptions or learning difficulties, and you give systematic feedback and reinforcement to students. And so this is where students use the 3 questions to give an explanation of carbon transforming processes. So it's still scaffolded, but scaffolding is removed a little bit, and students are able to write their own ideas to the 3 questions. And then there's fading, where students learn to do the task independently. So this is gradually reducing scaffolding and other forms of assistance. And so this might be where a student answers a test question that focuses on key student difficulties. So maybe a more open-ended question about where animals get their energy, let's say, or what happens when a flame burns, and what happens to the energy after a flame burns, for example. And so the fading occurs as students are taking assessments on the carbon transforming processes. And I'll just mention maintenance. Maintenance is giving students the opportunity to apply their knowledge in other contexts. So this happens, like, for example, in systems and scale, students learn about combustion, and then again in the human energy systems unit, they talk about combustion as well. For some of the other carbon transforming processes, they practice cellular respiration with animals, and then they'll practice it again with plants or with decomposers. So this is allowing them to revisit the things that they've learned multiple times throughout the year. But we're going to focus mostly on the model, coach, and fade parts. So in systems and scale, the application activity sequence for combustion occurs primarily in lesson 4.3. So the modeling phase occurs when students use molecular model kits, which is a highly scaffolded activity, to explain changes in matter and energy during combustion. And so they also use yellow twist ties, which they put on carbon to carbon and carbon to hydrogen bonds to represent chemical energy. And then they can physically trace matter and energy as separate entities. Additionally, here's an example of sort of what the PowerPoints look like. They're animated within PowerPoint, and so you can see molecules and energy going through chemical change. Feel free to go check this out now on the National Geographic webpage in lesson 4.3 in the PowerPoint, and you can see how this animation works. And then last, the coaching occurs when students explain combustion using the 3 questions process tool. So this is very small right here, but I'll show you what it looks like. So here are the 3 questions before and after a change. So just for fun, if you'd like to, you could pause the video here and give a shot at answering the 3 questions yourself for combustion and see what you would write into these spaces. Okay, so where are atoms moving from? So ethanol is moving into the bottom of the flame, and air, specifically oxygen, is moving into the bottom of the flame as well. And there are also, overall, more molecules moving into the air because the weight of the ethanol decreased after it burned. So for the second question about carbon, carbon atoms are in molecules of ethanol before combustion, and oxygen is also involved. And the products are carbon dioxide and water. And then for energy, before burning, the energy is in chemical energy, and then after burning, the energy is in heat and light, and maybe motion. Sometimes you can see that burning causes a little draft of wind that you can sometimes observe. Okay, so finally, to finish the application activity sequence, there's another coaching phase where students attempt to explain another organic material, methane, that also burns. So in lesson 5.1, there are activities where students practice explaining methane burning that are similar to explaining ethanol burning. And this is actually unique to systems and scale, that we have one more foundational knowledge and practice phase in this unit. The other units only have these at the beginning. But this is an important activity, very important, for all of the rest of the units, where students discuss the difference between carbon to carbon and carbon to hydrogen high potential energy bonds, and compare them with other bonds with carbon, like carbon to oxygen bonds and carbon dioxide. And this is where they learn to identify organic materials with carbon versus inorganic materials with carbon. And so this is knowledge and practice that's used throughout all of the units. Finally, the fade phase happens when students have the opportunity to practice answering the 3 questions with other examples of combustion. And the maintain phase occurs, again, when students go to human energy systems and talk about combustion of fossil fuels on a global scale. Okay, so I want to mention again, the Carbon Time Activity Sequences document has a table that looks just like this, and it shows the activity sequences in the other Carbon Time units at the lesson level. But the most important thing after all this that you need to recognize is that when you're doing the PEOE inquiry sequence, that students start by expressing their own ideas. And as a teacher, you allow them to do that and create a space and a welcoming space for them to do that. And then, as the activities progress, students need to modify and change their ideas based on the data that are collected. So they could be expressing ideas that are wrong at the beginning. It's hard to step back and let that happen, but then as they collect data, they can modify their own ideas. And the data should be able to tell students whether their ideas are correct or incorrect. And then when doing the application activities sequence, students start with highly scaffolded ideas where the teacher is modeling and students are using tools to help. And then by the end of the application activities, students should be able to give a good answer that includes the atomic molecular level with less support. Okay, one more thing before I sign off. There are activities in each unit that are designated as optional. You can read about why these are optional in the Units at a Glance document, and as well in the background information that's located on the National Geographic site for each lesson. And there are two reasons why an activity or part of an activity may be optional. One is that the material may be either too easy for high schoolers or too advanced or detailed for middle schoolers. And the second reason that we've designated things to be optional is because there are certain things like the molecular modeling activities that we consider to be sort of modular. So for example, students learn about cellular respiration in the animals unit, the plants unit, and the decomposers unit. So let's say you're teaching all three units, and in the animals unit you teach that first and you do cellular respiration in depth using the molecular models and the animations and all the PowerPoints, and you have, oh yeah, I have it here, and you have the students give an explanation using the 3 questions. And then maybe you teach the plants unit. And so what we recommend is that you see how they do on the pretest for cellular respiration and find out how are they doing now with cellular respiration. Maybe they know a little bit more, but maybe there are still some problems. So let's say then you choose to skip the actual molecular modeling with the molecular model kits and just do the PowerPoint animations that show the chemical change at an atomic molecular level, and then have the students give an answer to the 3 questions. And then let's say you do the decomposers unit. And again, we ask you to check how they did on the pretest. So maybe they're mostly all getting it this time, but now, so you decide now when you do cellular respiration, you might just explain how decomposers are similar to other living organisms in that they do cellular respiration and fill in some of those details. And then you jump right to the students answering cellular respiration in terms of the 3 questions. So for all 3 units, we have the full suite of activities for cellular respiration, but we'd like to indicate to you as a teacher that you should do what your students need in order to do a good job of answering the questions and explaining cellular respiration. Okay, so thanks for listening. The next part of the workshop, if you're doing everything in order, is to look at your own students' responses related to a particular unit and then go through the unit. So I'd like you to spend some time thinking about the inquiry and application activity sequences, especially examining the learning goals for the students for each unit, and see if you can link them up to where specific learning goals are assessed. Also, you can complete the inquiry investigation in your own home. Are there any details at all about the methods or materials that you'd like to be clarified? And try out the molecular modeling activity so you can get a sense of what will be easy or difficult for your students. Definitely check out our new videos and new PowerPoints that have jazzy animations. They're really cool. And I hope that you enjoy your explorations, and don't forget to email if you have any questions. I'm always happy to set up a phone appointment to talk if you have a lot of questions that are hard over email. And feel free to post on group spaces about your experience doing the inquiry investigations, or if you have any questions. So thanks very much. Thanks for listening, and I hope you have a great time. Bye.